Hi, welcome back. Let's carry on now. We're going to do a load of examples using some of the common chemicals that we talk about. We're going to look at this Lewis and a new one, Cooper diagram. What is a Lewis and what is a Cooper diagram? Well, first of all, these are just ways of diagrammatically representing all of these chemicals that bond like this or like that, or even with that and with something else over there. It's a way of representing it, because drawing these shapes can be very taxing. Let me put it that way. Nigh on impossible in many cases, in fact. Okay, so because we don't draw three-dimensional shapes well, what we're doing is we go and to boot, they're different size atoms, and they orient themselves in different ways. We can have three-dimensional setups with this, which we do in fact get, right? Now, let's just have a look here. The Lewis and the Cooper diagram are two separate ways of diagrammatically showing how we put them together. All right? Let's just take a few. Now, first of all, a Lewis diagram, okay? Now, what we do is when we're going to put these atoms together, we draw each one, right? On the Lewis diagram, we represent the electrons by dots and crosses, all right? Or dots and plus signs, okay? The Cooper is represented by lines, okay? Don't worry, I've got 1s, 2s, and 3s there, all right? That's just indicative of something, all right, which we'll get to. The first phase of this is to say, let's look at a few typical examples. Let's look at water, all right? Let's look at water, okay? H2O, right? Now, go through these with me. Let's write them down, okay? Let's go through them together. H2O. Well, first of all, let us look at the electron configuration of hydrogen. Well, we know we've got hydrogen in here, and we know that is 1s1. We know that that looks like that, correct? Okay, let me draw my arrow a little bit better. We know that we've got oxygen in there, and we know that oxygen, okay, is in fact element number 8, which means 8 protons, therefore 8 electrons. And let's have a look. It's 1s2, 2s2, 2p4. So let's draw it. 1s2, 2s2. There we go. And now we're going to draw 2p4. 1, 2, 3, 4. 2p4. Now, when we draw this in a Lewis or Cooper diagram, what do? We only draw the valent electrons, the ones in the outer shell. Okay? We only draw those. So if we've got, these are then in the core. This are the valent, this is the outer shell. We draw all of them, all right, in the outer shell, right? So over here, we have got 6 of them in the outer shell, 4, 5, 6. So what do? We're going to go and we're going to draw those in. So we represent them, okay, on there. Now let's choose. So let's go to hydrogen first, all right? Let's say hydrogen, I've only got one, so I'm going to represent you with a dot. I start at the top and work clockwise around, okay? Oxygen, I've now got to represent you with a cross. So I've got to put in 6 electrons, 4 in the P and 2. Those are my outer shell. 1, 2, 3, 4, 5, 6. Right, now can you see what we've got? Let's just go. Remember we said we had 2 open spaces, non-metal, going to take the electrons. Here they are, right? There's the 2 open spaces. There they are over here. Can you see them? There's a space for an electron to come in next to that one, because all of these electrons are represented by the cross. Okay? Well, that means that hydrogen can come along, can't it? And it can share its electron, and this one can share its electron. So that is what we draw. There it is, right? What I'm going to, let me draw it, okay? That H plus actually would move just a little bit closer, and I wouldn't have that line. We would have, let's go back and put it in black, H over there with its dot there and that H dot over there, right? But now that shows us all of these crosses and dots are electrons. So what have we got? 2, 4, 6 electrons from outer shell of oxygen, right? And 2 electrons, those are our crosses, and 2 electrons from the hydrogen to fill in those spaces, right? Oxygen was, remember, its position is at -2, hydrogen +1. Okay? We are going to talk about electronegativity a little bit later, how to put these. But it's just a recipe. So you can see we've got those in it. Okay? That's what water looks like. Now, how do we draw the Cooper diagram for that? All right. Well, basically what we've got is we've got O over there, and we've got an H there and an H bonded over there. This represents a single electron bond. This is also a single electron bond. Okay? Why? Because one electron is bonded with another electron. It's not a double. One electron is sharing with another electron, either covalently sharing or ionically being taken. But there's an electron that sits over there. One electron has been given from one to the other. All right? Now let's just go back up where I drew all those. Can you see here? That is a single electron bond. This is a double electron bond. I'm going to explain these later. And this is a triple electron bond. 3 electrons. You'll see that in nitrogen. Okay? Let's continue. All right? Let us now look at another common one. Carbon dioxide. Okay? Let's look at carbon dioxide. Okay? Carbon dioxide. CO2. Carbon, 2 oxygens. But now, these two, how do we draw it? How do we represent it? Okay? Well, what we do is we say, first of all, di. Di means 2. In chemistry, tri, and in tri means 3. Tetra means 4. Carbon tetrachloride. We're going to draw that one as well. Carbon tetrachloride, tetra, 4 chlorines, carbon with 4 chlorines. Okay? They'll go through in class in your textbooks. There's an absolute way of naming these, and you just got to learn that and go through. With a bit of practice, it comes very quickly. All right? So we've got that. So let's have a look. What does carbon dioxide look like? Right. Now carbon, if we draw it, carbon, okay, and we go over here, is 1s2, 2s2, 2p2. Okay? So have a look again. Let's have a look here. These are the outer electrons, aren't they? So therefore, we've got to draw carbon, just the valent, just the outer shells. Carbon looks like this. 1, 2, 3, 4. Okay? Now, carbon here is going to have oxygen with it. All right? So what do we get here? Okay? All right. Carbon dioxide. Now, oxygen is 1s2, 2s2, 2p4. So let's draw oxygen. Okay? So we say 1, 2, 3. Remember, we're drawing these guys, so we've got to do 6. 1, 2, 3, 4, 5, 6. Check. Yes, it's left us with 2 open spots over here. Okay, those are our valency -2. There are 6 valent electrons or valency electrons, but the valency is -2. Okay, so what happens? Well, carbon has got 2 spare there. Oxygen has got 2 holes that it will take. Now, here's where we have to say, right, we say, okay, in this case, this one, okay, that's fine. This one is the most electronegative. Have a look. You'll see that it is more electronegative than carbon. Okay, I think the oxygen's 3.5. Not 100% sure right now what carbon is, but it is more electronegative. So we say that this one, therefore, rules. We use the valency of the most electronegative -2, which means carbon in this case has got to be the positive one because there's no charge on CO2. It's a neutral molecule. So carbon is equal to +4. We take the most electronegative, the oxygen, -2, okay, because that's the one that governs now. So our carbon has got a valency of +4, which means there's 4 electrons it shares. So what happens here then is this. All right, our carbon and our oxygen get together. All right, carbon, the oxygen, remember carbon is +4. So the oxygen, I'm just going to draw that guy there and that dot there. And we've got cross, 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 cross. And the oxygen goes this side. And we say, okay, double, 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 single, single. And what happens here is this. These guys get together. Okay, there's a share. These two share. This one shares with that one, and that one shares with that one. So how do we write it now that we've worked out how it works? We say carbon, X dot, oxygen. Whoops, just make that a proper solid dot, like that. And you are now complete like that. Okay, whoops, sorry, he's gone, right? Because he's moved across here. This one, the carbon over here, the carbon has done that there, and the oxygen over here has got a dot and a dot, and we've got those left there. That's how we draw it as a Lewis diagram. The Cooper diagram is C, O, okay, O. But now how do we draw it? There's a 2-electron bond like that, right? So we've got, can you see? There, let's just highlight it. There was 1 electron, there's another electron bond. So we've got on each side a double electron. So this carbon here, it's 2 electrons, and 2 electrons have taken the 2, they've shared those 2, right? The other side, he has shared those 2, right? Like so. That's what it looks like actually, right? We've got the carbon, the oxygen, carbon, oxygen, 2 electrons this side, 2 electrons that side have been shared each way. So that forms CO2, right? Now, let's have a look at another one, all right? Let's look at nitrogen, all right? All right, nitrogen, do another page. Nitrogen. Nitrogen, if you remember, oops, let me just make it a little bit better visibility. Okay, what have we got here? Nitrogen, okay, was a -3, wasn't it? Now we know that nitrogen exists as N2 because, to reiterate, it's diatomic. So what are we saying? Nitrogen looks like this. All right, nitrogen is it's got a triple. It's 1s2, 2s2, 2p3, right? So we've got 5 electrons around each nitrogen. 1, 2, 3, 4, 5. Can you see the 3 gaps, the -3? There they are. The -3, the valency. We've got 1, 2, 3, 4, 5 valency electrons, but the valency is -3. Then we've got the other nitrogen next to it, over here. He's got 1, 2. Also available is 3 spots. There they are. So what happens? How do we form N2? Obviously this N and this one get together. They do get together and they form nitrogen like this. All right. And what have we got this side? We've got a dot and a cross, a dot and a cross, a dot and a cross, right? And over here on each side, we've got these 2. Now, just as in a slight aside, these over here that don't bond are called lone pairs. They're a pair of electrons that come with, in this case, it was these guys, wasn't it? The 2 S2s. They stood there, right? They are a lone pair of electrons. They play a big role in the shape, which we do next year in grade 11. But we need to recognize that we've got them. These are the bonding electrons over there. So how do we draw this as the Cooper diagram then? We say, right, you're nitrogen. We only actually show the bonding electrons. In the Lewis diagram, we show all of the valency electrons, the valent electrons. In the Cooper diagram, you only show the bonding. So we've got a triple bond over there like that. Okay? These electrons come together like that. So these are the bonding electrons. We leave out the lone pairs in the Cooper diagram. Okay? Now, I need to do with you, all right, okay, carbon tetrachloride and methane. Okay? So let's just have a look. Now, carbon tetrachloride, okay, okay, all right, we've got water there, carbon dioxide, nitrogen that we've done, all right. Let's look at carbon tetrachloride. What is carbon tetrachloride? It is CCl4. It is the chemical that's used in dry cleaning. It's got that distinctive smell, okay, that when you walk into many dry cleaners that still use it, I think they're probably using others nowadays. I don't really know. But in essence, it's that distinct dry cleaning smell. Carbon tetrachloride has been used in there. As I say, today you might not get that smell. They might have deodorized it or whatever the case might be. You still, the other day I noticed you got dry cleaning patches, like little tissues. They had that smell of carbon tetrachloride. But be that as it may, okay? How does this look? Well, carbon, we know, okay? We say, right, carbon, you've got 4, okay? My little things have turned into a plus sign, I think, there, because I'm writing slightly at an angle. And chlorine has got a valency of 1. So what is going to happen? 4 of them are going to come in, so it's going to look like this, isn't it? 1, 2, 3, 4, Cl, 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 and Cl. It's going to look like that, right? Now, how do we draw this? Well, we draw it like that. We're showing all the electrons that are involved. But the interesting thing here is it's drawn like this, C, Cl, 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 Cl. Can you see a 1 electron bond, okay, on each let's say side of the carbon? What happens here? That's the Cooper diagram, that's the Lewis diagram. The interesting thing here is we assign electronegativity. Chlorine is more electronegative. Actually, let me not abbreviate it like that. More electronegative. Okay. Therefore, we use its valency, right? Remember, we say it's more electronegative than that. Therefore, we use Cl, and Cl is -1. Therefore, carbon is going to be +4. So we're going to have 4 chlorines coming in there. Okay? Now, let's have a look at methane. All right? Methane. Methane, formula CH4. Now let's have a look. Carbon is more electronegative. So therefore, we use C-4. Similarly, hydrogen. Let's look at hydrogen on its own. It's 1s, not 1si. It's 1s1, isn't it? Okay. It's only got 1 electron to give away. Therefore, hydrogen is always going to be +1. Okay? Because it's only got 1 to give away. So therefore, hydrogen is going to be +1. Why do we have 4? Well, because we need 4 of those to balance that -4 out. Can you see now that carbon once again is looking like this? Hydrogen, H, H, and H. So we have like this. This is the beginning, by the way, of something called organic chemistry. Organic chemistry. Okay, a lot of rules, recipes there. Okay, that's there is, see, it's methane. It's the gas that we use. Okay, the gas that in coal mines that keeps it burning or for years. Okay, that was responsible for miners' deaths many years ago. So what happens is, can you see the difference here? Carbon over here is -4, but carbon was +4 in carbon tetrachloride. That is why above the carbon we wrote a +4 or a -4. Carbon can be both. Okay? It can be both. It can be a plus or a -4. Okay? You might ask me, can oxygen and fluorine combine? Yes, they can. Most definitely. Right? Oxygen and fluorine can combine. So what have we got? We've got fluorine, if you remember, fluorine was -1. It's more electronegative than oxygen, so the fluorine is actually going to take electrons from the oxygen. So we're going to have oxygen over here at fluorine is -1. How many spaces has oxygen got? Let's have a look. Okay, oxygen was 1, 2, 3, 4, 5, 6. Remember, oxygen has got 2 parking spots, but it's also got 2 electrons it can give away. So in this case, the fluorine, because it's greedy and it's got a higher electronegativity, it hupses or takes away, it pinches the electrons from there. So these electrons over here go over to that, and we get a molecule which is OF2. All right? So yes, we can have that. We can have, because the fluorine is so negative, so electronegative, such a greedy element that it pulls electrons even from the one next to it, the oxygen. Okay? Right. Let's just have a quick look at another one. We've looked at that, oxygen. Oxygen, just on its own, just a quick look. Okay? Oxygen is -2, and oxygen on itself is -2. So what actually happens over here, let's get rid of that. We'll say oxygen, 1, 2, 3, 4, like that. This oxygen looks like this. Okay, and we get, hey presto, we get a bond and a bond. So we get O, double bond O. Okay, because we've got here a double bond, right? 2 electrons, there they are. these two and these two. It's not 4. 2 electrons are being shared over there, okay? Let's have a look at another one. For example, ammonia, okay? Let's have a look at ammonia, all right? Okay, it's NH3. Nitrogen, remember, has got 1, 2, 3, 4. There's our valency electrons. It's a -3, remember? -3. Hydrogen, we said, was always a +1, right? So you can see hydrogen, hydrogen, and hydrogen, right? Once again, what do we call these guys up here? Let's just recap it. These are lone pairs. Those are the guys that sit in the, no, they don't bond. They are usually the 2s2, the 3s2, the 4s2s, okay? They're the ones that are in the valent electrons, in the valency electrons, but they're not valency, in this case, is -3 of nitrogen. So there we've got that. How do we represent that in terms of the Cooper diagram? NH like that. Okay. Can you see this is like a stick diagram that we're using? All right. Have I got another one here? Yes, calcium fluoride. All right. Let's have a look. Okay. Calcium fluoride. Now we've got calcium and fluorine getting together. How does it do it? Let's have a look. Calcium is +2. Fluorine -1. Therefore, we need 2. We need calcium and F2. Okay? CF2, because we need 2 of those to fill in. Why? Let's have a look at what is the diagram? What does calcium look like? Okay? Calcium, we said, was number 20. All right? Very important thing coming out. 1s2, 2s2, 2p6. Okay, we've now got to 10 electrons. Okay? So we're going upper level now. 3s2, okay, 3p6. So let's count. We've remember S, S, P, S, P, right? The next orbital will be the D. We go S to P to D. Okay. In some of the extra more advanced ones, I'll go into the higher orbitals, but SPD. But now, before it fills the D, it fills level 4S. So we go 3S, 3P, 4S, 3D. It takes a lot more work to put one into this big D orbital than to fill the S, because the S is small. So we've got 4S, let's count. 8, 10, 18, 4s2. So now we only count the outside ones, okay? Which means, what does calcium look like? Okay, calcium actually looks like this: 1, 2. Fluoride, fluorine, has got 1. So we've got a fluorine and a fluorine there, CaF2, right? So we draw that. Sorry. Okay. Okay, like so. Basically, that's those examples. The next one is going to be substances and structures, okay? And I'm going to focus there. There's a lot of things about allotropes and things. We'll talk about that. Talk about buckyballs, okay, which is a carbon formation. But I'm going to focus on electrolysis of water and then chemical change. We're going to start getting into chemical equations and working out how much of this do I need to add to that with a pinch of this and some of how much do we need to come. We're actually going to start essentially baking the cake. Okay? We're going to start putting recipes together for making carbon dioxide, magnesium oxide, calcium fluoride, and ammonia, and all of these things. We're going to put recipes together now, okay? And then we're going to see how much do I need to add of this, because that's important, okay? I do apologize that went over, but I think it was a good session to end off that before we start the next session. Thanks for watching, and I look forward to sharing the next portion, which is the really great part, where we get to do some mixing and matching. Thank you.